This is Unit 2, Problem E on the AP workbook. There's two blocks being pushed by a person, and we can draw the free body diagram. We want to draw it as much to scale as we can. We're focusing just on this guy here. So you have the normal force of the floor. You've got M1G. And then this one is bigger mass. It says so in the directions. So you're going to have the normal force of the floor too. And this will be FG2, which is M2G. Now, those have to be equal and opposite because it's not moving up and down, right? This is equal to 0, and acceleration is equal to 0 on the y-axis. On the x-axis, however, they tell you that it begins at rest, so it's accelerating. So you have V and A. So you have to have a net force of 0 on the y-axis, but you're going to have a net force to the right on the x-axis. And this is important because if they want you to draw it to scale, right, they want it to reflect the relative magnitudes. So the block 1 has to have a force from the push, this pushing force, which has to be bigger than the force back from this other guy. We'll call it the force from M2 on M1. But M2 feels a force from M1. That's got to be equal and opposite, right? So it's got to be the same size, but we're going to call it M1 on M2. These, according to the third law of motion, must be equal. So they're asking us to find the acceleration of block 2, but the acceleration of block 2 is the same as the acceleration on block 1. So we could actually just treat this as a whole system, and looking at it as a whole system makes these internal forces. And when you have internal forces, treating this as one thing, you'll just have the force of the push, you'll have the normal force up, and the weight of both pulling down. So that's actually an easier way. This is called system solving. That's what I call it. I don't think it's like a special name or anything. So when I write this, I'm just going to have F push equals M1 plus M2 times the acceleration. So the F push divided by the sum of the two masses is going to be your acceleration for both objects, not, for this one and for that one. So then they tell you they're going to add a third block. What's going to happen if this person pushes with the same force? Well, what happens to the free body diagram? Well, first of all, the free body diagram does not change except that now you have a third force. So nothing changes on the x-axis force. But now when you look at the y-axis force, you're going to have Fg that's due to M1, M2, and M3. So this is going to transform into F push equals M1 plus M2 plus M3 times acceleration. So when you move this around, you're dividing by a bigger number, which reduces the acceleration. This should make common sense, right? This is a physics proof for something you already know. When you use the same force on heavier things, it accelerates less.